So hi, everybody. Welcome to the Research Days talk for July. Today's talk is entitled Image Provenance Analysis for Disinformation Detection. A very interesting topic and an unusual one compared to many of the things that we often cover in the Red Hat world. We're very excited to be starting a new collaboration into this type of research, thanks to efforts by Walter Scheirer, who is the lead investigator at the University of Notre Dame. Walter is a professor, associate professor in the Department of Computer Science and Engineering, and his research is focused on primarily on the problem of recognition through algorithms and learning-based methods applied to both vision and language. We also today are welcoming Daniel Moreira, who is participating in this research as well. And he is from Loyola University in Chicago. And he is also investigating the same topics and has been a member of the Computer Vision Research Lab in the past. And finally, we have a Red Hat conversation leader to coordinate and help introduce the topic and ask questions. But we encourage anybody who's attending to either ask your questions in the chat, or you can join, because this is Hopin, you can join the conversation with audio and video at any time. Once in a while, Jason will ask if anyone is interested in doing that, and that will give you an opportunity. But if at any point you want to join the conversation anyway, feel free to appear or to send something in chat, and then Jason will invite you to join. So thank you very much for coming. Happy to see this new research starting. And Jason, please take it away.
Thanks, Heidi. So I'm Jason Schlessman. I'm a principal software engineer in Red Hat Research, and I'm happy to have Walter and Daniel here today to discuss the collaborative work that some of the collaborative work that we've been doing for, I believe, the past year. We have an interest in this area in part because we, as will be discussed, we sussed out and ascertained that there are enterprise aspects to this work that kind of blur the line between what academics are interested in and what we at Red Hat are interested in. To that end, we at this point have one upstream contribution from this collaboration, which is a Python toolkit library for image forgery detection, PyIFD, and we are working towards publishing some performance results on how that library performs compared to deep learning methods. Beyond that, I'd also like to virtually introduce Bill Theisen, who is in the chat, and he will be keeping an eye out for questions that come up beyond, in case I miss anything. He is Walter's grad student, and he also, we're very fortunate to have him as an intern at Red Hat Research this summer. So if you see responses coming from him, he's not being a know-it-all. He does know a lot, but he has been recruited to fulfill this role. So with all that in mind, Walter and Daniel, I thought that what might make sense is, before you guys dig into the presentation that you have for us today, we can look at the title of the talk and parse out what the words are, but perhaps you guys could give a succinct definition of just image provenance analysis to start out.
Yeah, absolutely. So first, I just want to thank Heidi and Jason for setting up this talk. We're really excited to share our research with Red Hat Research and the broader company today. This is a really, really great opportunity. So to begin, let me give a brief definition of what image provenance analysis is. Simply defined, it's tracing the historical lineage of a digital image. Now you may be wondering, why in the world would anybody want to do that? Well, it turns out these days on the internet, images aren't always the original scene that was captured by a sensor. And in fact, in some cases, they're not always real images. There's a lot of synthetic media out there. And importantly, there's a lot of remixed content, right? Somebody takes an image, reworks it, shares it, it's reworked over and over and over again. So the idea of image provenance analysis is that this is similar to what is done in the fine art world when you're trying to trace the provenance of a piece of artwork. You want to know its history. How many owners did it have? How much change did it undergo over time? If you can document that, you have a better idea of the evolution of the information represented by the painting, or in our case, the digital image. So these things are very much intertwined. Now, the second part of this title of the talk is about disinformation detection. Where does that come into play? Perhaps not news to anybody on this hop-in event. Disinformation is a big problem these days on the internet, and a lot of it has to do with visual communication. A lot of disinformation is moving away from the purely textual domain to this visual domain, where you see this remixed content being remixed in ways that's malicious, right? So then it comes down to understanding what changed, and is the message something we should be worried about?
Okay, great. And we already have a follow-up question that I'll put out there. So thanks for that explanation of image provenance analysis. Ari would like to know what your definition of disinformation is in this case.
Ooh, that's a good question. What is disinformation? So now you get deep into the sort of mass communications aspect of this particular problem domain. I would say disinformation, at least this is how we define it, is it some malicious message, right? Something that is, number one, not true, but number two, is meant to influence behavior in some anti-social way, we'll say. Now, of course, there's a lot of fake stuff on the internet, but most of that is not of interest to this particular problem, right? Jokes, right? Again, think about content like memes, right? A lot of this stuff, right, of course, is not real, but it doesn't really provide any sort of social threat. So what we're interested in here, of course, is political disinformation, information that is threatening, say, public health, right, which has come up quite a bit. And Daniel will have a little bit more to say about that as we go on today. That's a great question.
Yeah, so then, when you guys first talked to me about this, however long ago that was, first thing that popped into my mind was social media and media in general. But I was surprised to hear that there were other aspects that would be useful for this. So yeah, can you guys share a little bit about where else this would be applicable beyond media and social media?
Yeah, sure. First one that comes to mind is an intellectual property protection, right? So imagine that you have an account to Flickr and post your pictures there, and it's yours, and somebody takes it and you're not even aware that they're using your content without giving you credit. So provenance analysis in this sense may be a way that can help in finding these reuse and give the due credit of usage. Another one application that we have we've been working with and have some interest is scientific integrity. So what happens, imagine that you're a researcher working, especially in these last times with COVID, and you're writing a paper about the drug that you're developing for treating COVID. And as part of your paper, you're generating images of X-rays of lungs, and you want to provide these as a result of your paper on how you are managing the drug, and you're seeing improvements in the lungs. So some researchers out there, they're writing these papers and they're forging these images. They are generating fake images or reusing images that are not, that belong to other works that do not belong to them, and they're claiming as their results. So in the past 5 years, just to give you an idea, the number of papers that were retracted, that were removed from circulation because of problems with images, it doubled. And provenance analysis comes in handy in this work to find these images that are being reused and claimed as false results.
Okay, got it. Thanks. We have another question in chat, and it kind of ties into something I was going to ask about as well. So, I've been thinking when you first told me about this, and I was thinking about why this is more prevalent of late, it seems. And empirically, what I thought was that this used to be sort of a niche thing. Like you really had to be skilled in Photoshop or something similar to make a convincing fake. And there's more, for lack of a better term, tools available now, in apps and websites that let's say make it easier to make a fake. And beyond that, Ben is asking if a model like Doughty makes this sort of detection harder or easier with respect to detect if it's possible to detect something that is coming from Doughty as opposed to another model.
Ooh, yeah, that's a really great question. So we're definitely interested in those types of generative models here in a forensics context. I think the good news is since that generates content that is not quite 100% synthetic, right? Because it's trained on natural images, but it's these synthetic compositions that tends to be very easy to detect. Compared to, say, taking an image that came from a digital camera and replacing one small patch in the image, right? Perhaps a small object in the image, right? That's a much more difficult problem. And the latter is more of what we're focused on in the work we're going to talk about today. But I'll point out the technology gets better. You can imagine developing adversarial algorithms that try to synthesize content that matches the pixel statistics of a digital camera, right? Then it's going to get a lot more difficult for us to perform these analyses. Really, really good question.
Okay, great. Thanks for that. And to that end, since you mentioned generative models, would that also include GANs in the statement you just made?
Yeah, absolutely. Basically, any machine learning model that produces content as output instead of something like a classification decision. And of course, right, that's all the rage in machine learning, right? Obviously, just a tremendous number of papers every day hitting, sites like Archive, which hosts preprints of emerging research. All the major conferences in machine learning are just churning out new algorithms to do this, and there's tremendous interest. And of course, not all that is bad. Probably 99% of it is being used in creative ways, which is really great. But it's that that small fraction, right, which turns out to be huge in terms of numbers that we have to worry about.
Okay, great. So I guess the only other thing I'll point out before we can get into the actual slide part of things is, are there solutions to this right now? I mean, I would think that, especially if we're talking about social media, we would expect some of the heavy hitters to have something out there already that, even if it's not open source, publicly available, that they would have an answer to this already. Is that the case?
Oh, this is a good question. It turns out, no, there is no turnkey solution anywhere out there to basically flag content as containing a potentially alarming message. For a number of years, there has been research in this area, going back basically to the mid-1990s. Right, this field of media forensics appears, coming out of signal processing to try to create algorithms, right, that can detect manipulations of some form. But there have been a number of hurdles in terms of getting something that's like a commercial product, right, or even something that's in-house at one of the large social media companies. Part of that has to do with the vast number of images that are being uploaded to these sites. For instance, the Facebook core platform ingests something like 2 billion images per day. So that's been a constraint when we think about the runtimes of different algorithms. And also, again, their effectiveness. Yeah, we work on this. Yeah, we're proud that we're making good progress on the problem, but there's nothing that gets you to close to 100% accuracy, right? So that's been a struggle. You don't want to mistakenly flag content as being, malicious, or you don't want to miss stuff, right, which is potentially involved in some sort of disinformation campaign, or again, perhaps one of these doctored scientific images when you have a scientist who's trying to fake the results and get their paper published. So we're not quite there yet, right? So there's a lot of work to be done, but that's interesting. And I think that's kind of why we're having this conversation, right? Where can we build collaborations to engineer better solutions to chip away at this?
Right, and so that's why we've had the current collaboration, right? Since these are enterprise level problems, and I believe you guys have identified the pinch points to that respect. Is that right?
Yep.
Yeah. So it'd be like quality of service, latency, and scalability, correct?
Yeah, and scaling is, I would say, the major problem. So as Walter just mentioned, you have Facebook billions of images a day. Take Instagram, 95 million images a day. So how can you process these in enough time and good way? So scaling is a problem. Of course, I can see on the basic solutions ways of where you can just let the computers run things in parallel and have fun outside, of course. But the questions that stays is when you have this volume of data, if you are effective enough, so if your results, they make sense, if they're correct, if you're not missing anything or pointing out things that are false positives, of course. And also if you're processing things in enough time, so you have an answer that comes in handy when you really need it. So these are the challenges that we need help, and we have space for collaboration.
Right. And then beyond that, I mean, right now we're just talking about images. And so if we start thinking about videos, it takes it to a whole other level of skill, right?
And we have some examples to show you about it. Yeah.
Okay. So I want to give you guys enough time to present your slides, but we have one more question before you guys get started on that. Oh, Bill answered it. Cool. Thanks, Bill. All right.
That's why he makes the big bucks.
Okay, Alex has a question which we've discussed actually on protecting against adversarial use of these algorithms. And I believe you guys may touch upon that in your slides. So I'd like to just let you guys get started. And if we don't get a satisfactory answer from Bill or from you guys, then we'll revisit it.
Okay, that sounds great. All right, then I will jump right into it. So in this first part of the presentation, I'm going to dig into this definition of provenance analysis a little bit deeper. I'm going to try to give some visual examples and walk everybody through this. And then we'll pause for some more Q&A. And then Daniel will dive in even deeper and talk about the algorithms that we've been developing to chip away at this problem. All right, so part one. Provenance analysis. What exactly is this? We like to say this is also about telling the story of composite images, right? These are the images that we're really interested in. So the problem, again, we sort of touched on a little bit of this in the intro conversation. There are software packages, right, out there that are very popular, tools like Adobe Photoshop. And as I mentioned, right, this is a creative tool, right? Most users are having a lot of fun with this. We use this all the time in our own work, for perfectly, innocent means. But right, there is a small fraction of the user base that is doing inappropriate things, right, with Photoshop. Again, Daniel mentioned a great example, like the scientific integrity problem, which we'll talk about as we go along in this talk. Also, right, which was raised in the conversation, this notion of AI-generated photos, right? Synthetically generated media coming out of these new generative models, right? The internet, of course, provides us with so much training data. It's not that difficult to do this anymore, right? This seemed amazing a decade ago. Now, there are plenty of models that are just automatically generating this content. Websites like thispersondoesnotexist.com, where you can just, forever reload the page and get faces generated by StyleGAN2 and other recent generative models. And what has been noticed on the internet is these synthetic faces are starting to appear on things like LinkedIn profiles, being used as part of a scam, and that is problematic. We've even seen this with fake scenes, like fake hotel rooms, fake Airbnbs. There's another website similar to thispersondoesnotexist.com called thisrentaldoesnotexist.com. And of course, right, deep fakes, right? I think we're all familiar with this phenomenon, right? Where it's like you're reanimating a video of somebody or taking, somebody's face and putting it on another body, right? And trying to reanimate it so it's naturalistic, changing the audio. All of this content is out there on the internet. From our perspective, though, again, like thinking about specific problems like image analysis, like single image analysis, this scientific integrity problem has been on our radar, and we've been working on this because this is a growing problem. And this is a clear case where, again, you don't have to worry about politics, right? You don't have to worry about the interpretation of a message. Is this satire or is this like a dangerous political message? This one is a bit more clear cut. There is a scientist who is not ethical. They are fabricating data. They're putting that into their paper or their grant proposal, and they're trying to get this material accepted by other scientists, by funding agencies, et cetera. That, of course, is a big problem, right? A huge ethical problem. And so what's driving that, again, the pace of science, right? Especially when we have challenges like the COVID-19 pandemic, where there's a lot of incentive to get material out as fast as possible. Again, some people are trying to cheat the system for personal glory or financial gain. And there have been a number of cases of this, cases that have been raised to the federal government here in the United States, organizations like the National Institutes of Health, the Department of Health and Human Services, right? They investigate these cases, and there are a bunch of, again, that are public. Papers get retracted, right? If there's conclusive evidence that something like this has happened. This has put a tremendous burden on scientific journals, right? Everything from the glam journals, right, like Science and Nature, at the top of the food chain, to just ordinary journals, right? That or in any field, right? We're seeing more and more of this content, right, being spread, which is problematic, extremely problematic. So what do we do about this, right? We probably need some sort of automatic triage to sort through this content and flag stuff, right? That won't be sort of pulled automatically, but we probably want a human in the loop to look at it further to see, if there really is a problem. Okay, so I'm going to talk a bit about the what here, what is provenance analysis, and then I'm going to start talking a little bit about how we do it in terms of data, and then, like I said, we'll pause, we'll have some more conversation, and then Daniel will pick up and talk about the algorithms, and then we'll suggest, some future areas of research, especially on the systems side of things, right? Because I know this is very much a systems audience. And again, you both need, you need these two pieces. You need both the algorithms, right, the computer vision, the machine learning, and you also need the back-end infrastructure. As Daniel mentioned, right, scale is a serious challenge here. So we're going to talk about all of that. Okay, so let me begin with this example. So here we have a cropped portion of a digital image, right? And this appears to depict two famous figures from the 1990s together, right? Two figures, perhaps, again, if you're from that era, you were a music fan back in the early 90s, you recognize these two figures. This would be kind of a surprising juxtaposition. We've got the notorious B.I.G., and he appears to be in the same car as Kurt Cobain. Again, coming from very different musical genres, and this is kind of this question that is in our mind when we see this, on social media, perhaps this is circulating. Did these two guys ever hang out in person, right? That seems like it would be amazing, right? Like a huge moment in music history. Well, it turns out that this did not actually happen. And so this is a really good example of the type of image that we're interested in when we're looking at doing this analysis, right? So we have Biggie here in one vehicle, and we've got Kurt Cobain and some other guy. I think it's like Pat Smear or somebody from the 90s as well. That they're next to each other. And again, you don't even see that other guy, right? So the image that Kurt is in is what we would call the host image, right? So he's originally there. The background is authentic, but Biggie has been copied out of his original image and pasted into this scene. And whoever did this did a reasonably good job, right? If you look closely, it looks plausible, at least right on first glance, right? So the challenge here is how do we create an algorithm that can, right, perhaps detect tampering, but then we want to go beyond that, right? Not just that this image has been modified in some way. If it is a composition, where did that other content come from, right? Can we figure out of a pool of large images what those images are? And then if this has been remixed, right, over and over and over again, can we put those pieces together to build a timeline, right? To understand that this edit was made, then that image was edited again, right, ad infinitum. And so we can see again another example here. We've got Tupac, who has been inserted into this image, right? So these things can become increasingly complex. And again, if you're familiar with the internet, especially internet humor, you must have seen images like this before. Right? Like memes follow this scheme. This image is kind of somewhere in between, you know, like visual disinformation and a meme. But of course, it's innocent, right? The world is not going to end if this image circulates on the internet. Perhaps it'll be a confound to a music historian, but you know, for the most part, you know, this is not a threatening message. But again, I think it's a good example of how this works in practice, right? And again, Tupac, basically his head has been inserted into this image. Okay, so once you have a collection of images, as I mentioned, you want to put them in order, and this is what we call provenance graph building. So you can reduce this to a graph construction problem. Once you have the images, right, figure out how they connect by establishing edges between the different images. And then this gives you a pretty good picture in terms of a human-based analysis of what's going on as this scene evolved over time. Now, coming back to the question of disinformation, right, I think we worry about things when they get political, right? So here we have a photo of one of the student activists from the Parkland school shooting that happened in 2018. And this activist appears to be ripping up the Constitution of the United States, right? Which of course would be some sort of, you know, polarizing, divisive image, right? For certain groups of people out on the internet. And when we see images like that, right? Like there's often, again, this immediate reaction to it, right, when we look at the surface level message. But looking at these two things together, right, if you know about the circumstances of the shooting, right, the politics of the activist, right, and the overall politics of America at this moment, we may sort of question this, you know, is this the right message, right, for this person, right, or is this something that is an inappropriate manipulation? And we can, again, go back to large pools of images, right, do our analysis and figure out that, there's an image that looks very close to this particular image, right, the same activist, the same paper being torn, but in this case, right, it's a target, which makes more sense, right, given what this activist is interested in, where they have appeared before in terms of the media. You know, that makes a lot more sense. We could also try to find right, some document, right, which has been inserted into here, and of course we find that as well out on the internet. So the idea again is, given some questionable image, you know, can we search the internet, find related images, right, and then build this graph to understand how this changed. Here's another example from the world of politics. We see a number of world leaders surrounding the president of the Russian Federation, Vladimir Putin. Now, this image is pretty famous, right? So hopefully this didn't fool too many people out there on the internet, because it was generated after the real event happened. So here's the original image, right? As I said, this is what we call the host image. The chair is empty, right? That was a seat for the United Kingdom. And this other photo of Vladimir Putin has been copied and then spliced into the host image, right? So again, perhaps not the most dramatic change to this image, but it does change the interpretation, right? It makes Putin seem like he's at the center of attention here at this meeting of world leaders, when, again, this never happened. And again, you see a lot of these subtle changes out there in manipulated content that has some political flavor. Okay, so moving on, how do we do this? Where do we even begin? Of course, it's the data, right? Most of what we do these days in computer vision, in any type of image analysis, even basic image processing, begins with some sort of data set. So a little history here. Our work in provenance analysis really ramped up in collaboration with a large government program that was run by DARPA called the Media Forensics Program, or Metaphor Program. This was a program that ran, I guess it started 5 years ago and it went for 4 years. As part of this, the National Institute of Standards and Technology, which is a government agency here in the US, which is heavily invested in evaluating different types of algorithms, right? You may know it from the crypto world. For a number of years, they ran a number of high-profile crypto competitions, right, where standards sort of came out of the competition process. The mindset here was similar. NIST created a challenge data set for a number of different tasks, and part of that challenge data set was image provenance analysis. And they released this data publicly, so anybody can grab these images and use them. And NIST is still evaluating algorithms too, which is pretty nice, that are developed around the data. But here's what the data are. So this was a data set that was not collected in the wild. NIST, in collaboration with some contractors, put it together. So people basically sat down with Photoshop. They took like stock images and they created these compositions. What's really nice about this data set is it has ground truth, right? A big challenge when you're getting data from the internet is, what was the sequence of events, right? Do we know what happened? With images in the wild, typically we don't. But I'm going to show you another data set in a second where we do have some sense of what happened. But that's kind of an edge case. So here, this is really nice. We've got ground truth edges. We know exactly what the manipulation type was. All of this is documented in a standard format, so it's easily parsable, and it's easy to evaluate algorithms. And some of these are really challenging, right? If you look closely at this image, you'll see some very small objects, right, have been spliced into some of the later compositions. For instance, right, one of the source images is this fly, right? So somebody cropped the fly out of the image, put it on the flower, right? And then that hand with the flower is pasted into another image with a pot of flowers. And this is where it gets really challenging because the small objects are hard to find, right? Bigger objects, it may be more obvious. And that is interesting too semantically because sometimes a change that is very small has a huge consequence in how we interpret the image. So this is a really good comprehensive data set. So this is one of the standard tools that we use for algorithm development. A data set, though, which is a bit more realistic in terms of what you see on the internet, is this one which came out of my lab, Reddit Photoshop battles. Here we went to the Reddit Photoshop battles subreddit. And if you're not familiar with this particular subreddit, it's worth checking out. Basically, right, someone Photoshops an image and says, check this out. What can other people do with it, right? And so you get these threads where somebody takes that original image and they modify it, and then someone else riffs on it. There's a lot of pop culture references, right? A lot of interesting remixing happening with these. This gives us not perfect ground truth, but reasonable ground truth because we have the timestamps from the thread, right? Which we can associate with the post that contains the new image. And so we can kind of trace the lineage that way and build a graph. As I said, this one's a little bit more realistic than the data set put together by NIST, which was basically just stock photos. Because again, this reflects internet humor, some of which is political and some of which does carry disinformation. With our collaborators in the political science department here at Notre Dame, the Koch Institute of International Peace Study, we've been looking at visual disinformation in joke form. Because it's not a joke when you get down into the deeper messaging of some of this content. So this is a great data set for studying all of that stuff. As Daniel mentioned, right, scientific integrity has been a huge focus of what our group has been doing. And we have a data set for that too. We've been poking into the scientific literature, looking at retracted papers, and also figuring out how these manipulations occur. These are a bit more subtle compared to meme-style imagery. A lot of this is these copy-paste operations in the Western blot images. These protein experiments that are very common for lots of different biological experimentation. Also, images coming from microscopy, people duplicating cells to claim that there's some effect, or trying to enhance the look of their particular method, which would not operate that way if you were on a bench trying to replicate the experiment. So these are all data sources that we're using to look at different aspects of these problems. Here's just another example of the scientific integrity data set. Scientific figures also tend to be manipulated, so it's not just about experimental data like the Western blots you see here. We also find matching correspondences between things like graphs, right? Human-generated figures, right? Where someone is just, copying a figure perhaps from another paper, could be their own paper, somebody else's paper from the scientific literature. And reusing this information, again, to make it seem like the experiment was successful, there was a big effect, when in fact it was all bogus. Okay, I'll pause here and we can take some more questions.
Great. Thanks, Walter. I'll ask a couple questions to get things going. If folks have questions, pipe up. Share your audio and video if you want, or put it in the chat, and we'll get to it. So I think what I caught from, full disclosure, I've never heard this presentation before. So I think what I caught was a sentiment of the scientific integrity work is a bit more of a tractable problem. Is that correct? As opposed to, say, the social media or socio-political work? Yeah,
absolutely. So number one, we're usually dealing with a small number of images, right? So it's, a corpus of papers associated with one particular researcher, or maybe, again, it's a larger pool of papers, but from one specific research area. And the way pure scientific fields like biology work these days, where it's like you have a cohort of researchers across different institutions looking at a very specific problem, right? So you don't have to go to the entire internet. You're not looking at, all the photos on Instagram, for example. It's maybe a collection of 100 papers, right? Would be like a big data set in this particular problem. And again, papers have a few figures, right? They don't have, thousands of figures in a single paper. And so that helps a lot. Number two, the problem is also tractable because it's more well-defined. It's like, did somebody inappropriately manipulate an image, right, in one of these figures that appears in the paper? And so you're looking for basically image duplication, right? There are well-known techniques in the manipulation detection side of things that can be brought to bear here. And then the provenance analysis is pretty tractable because, again, you don't have a large pool of information. And you also are unencumbered by, again, the interpretation of the messages. As I mentioned, the political disinformation is complicated because, again, parody and satire exist on the internet. Those are perfectly fine, innocent things. But they're often confused with disinformation campaigns, propaganda, et cetera. Here, we don't have that problem at all, right? It's very well defined in terms of what we're looking for and what the messages are.
And then are there, would you say, do you run into false positives in this area? Like the first thing I'm thinking of is like, say somebody, and admittedly this should be corrected, but I'm just thinking somebody gets like their latex tags wrong on their figs. And so, you have your model go through this and you say, okay, you find the section of the text that says in figure 5, this is shown. And then you analyze the actual image of figure 5 and it has nothing to do with, what the text says it has something to do with.
Yeah, so yeah, great question. False positives. Absolutely, there are false positives. This is why we think it's really important to always have a human in the loop, right? So you use these tools as triage, right? Then somebody has to sit down and look to see if it makes sense. Now, again, there are mistakes. We all make mistakes, right? So that's certainly a source of problems for these algorithms. But those are easily resolved in many cases. When you see, say, in a scientific paper that individual cells have been copied from another paper, it's harder to justify that as a mistake versus, oops, like we just added the wrong caption here, and we can, verify that these images came from our scope in the laboratory, right? We have the lab notebook, right? There's another chain of provenance, behind the scenes at the laboratory. So yeah, absolutely, like these things happen. Another general confound. Basic image processing operators. Imagine that somebody changed the contrast of an image. That could be in a scientific paper. That could also be, before I uploaded my image to Facebook, I wanted to make it look better, right? That's a global operation that does mess with the underlying statistics of the pixels, but it's not one that is typically considered to be malicious, right? It doesn't typically change the interpretation of the image. It could, depending on what's in the scene. Does it look a little bit more dramatic now, right? Because the contrast has changed. But in general, it's a bit different than these copy move operations that we're concerned about.
So I had a follow-up question. Before I do that, I'll just comment because I used to work in Woods Hole Oceanographic, and we often had several iterations of making the photographs that we captured with the microscope look better for publication. Even things like, what color is the background? So you're definitely right there. The question I had was a follow-up to Jason's first, which is, when you're thinking about papers, obviously we don't do a ton with images in a lot of the papers that we do, which are about performance and throughput and things like that. But we had another talk earlier that was about reproducibility for papers that were published, and how you would publish an entire data repository with results and all of the configuration information as an alternate way to look at whether anybody had changed the results in order to do the paper. Is it a faster way to handle the graphs as images and apply this to see if the images have been changed, or do you think that first method is better, easier, whatever? It's definitely not easy, but have you thought about comparing those two different ways of trying to do the same thing of verifying accuracy of a paper?
Yeah, that's a good point. So it's out in our radar because it depends on the figures we are processing. So as you're saying, if it's a graph, and whenever you transform a graph and you reuse it, you can change the scale. So it's better to analyze these in terms of data, the data that is behind that graph, right? So see if it follows the same distribution, or if it makes sense to be in the same distribution, have the same mean, same statistics, things like this. This is something that we're still working on and doing research and developing solutions. But yeah, Provenance will help us in the visual part now, but I see Provenance being extended to other types of media, and data in general is one of them. So yeah, analyze the data you have, see if it follows the same distribution. Does it make sense to follow the same distribution if it's different experiments with different sources? And then you can find mistakes or misconduct in this regard in the papers and guess what's going on.
Thanks.
Sure.
Then we have a question from Laura in the chat, and I believe I know the answer, but I'd like you guys to answer it.
Sure.
She asks if you guys envisage your analyses evolving to detecting malicious files hidden in images.
Detecting malicious file. So yeah, is this like steganography? So like hidden data in content?
Yes. Laura, if you want to share your audio and video, if we're not representing your question correctly, go for it. Oh, she says yes. There you go, guys.
Okay, yeah. So that is a manipulation. So it turns out there is a class of algorithms in the forensics world that is tailored to that question, right? Is there hidden information in an image? I think that could fit into this regime nicely because it's a series of edits, right? Now it's imperceptible to the human eye if it's done well, right? Modern stag tools are really good at hiding information. But I mean, we could flag in the provenance graph, like this looks visually similar, but like this change has happened, right? And it happened after the creation of the visual content. So absolutely.
Great, thanks. I think it's also useful to point out that I talk about our upstream contributions and like PyIFD, but and another artifact that's coming out of our collaboration is we're working on data sets together. And that I don't know how much that's been done in our group prior, but we're working towards publishing data sets with you guys, in part to assist folks outside of the hardcore engineering fields, like you had mentioned, the social scientists. Do you feel that that is going to have actually, let me rephrase that. What kind of value do you think that has relative to, say, like putting together a software library or an application?
Ooh, this one's really good. I think it highlights the interdisciplinary nature of this research. So as Jason just mentioned, yeah, part of our collaboration is collecting data, right? Curating data, and then ideally we're going to disseminate that data to other researchers, right, beyond our internal consortium so that they can work on it. The data set being referred to here is related to disinformation in that it's content related to the conflict in Ukraine. And so again, there's a lot of interest in the social media analysis associated with the conflict. But again, it's typically a lot of computer scientists jumping in, not quite knowing what to look for, like what the messaging really means. So our research group includes a number of political scientists and peace studies researchers, including Christina Hook at Kennesaw State, who's one of the few experts in Ukraine here in the US, Ernesto Verdeja in our Department of Computer Science, as well as one of the leads. They are great because they have contacts in Ukraine. We also have a research assistant who is Ukrainian, who helps us with the language barrier, right? Because a lot of the visual content has text overlaid on it. And of course, we're not Ukrainian or Russian speakers, though again, part of our consortium does do that. So that's helpful. They also bring to bear, right, a lot of intimate knowledge about the conflict, about the politics, especially the background to the conflict, right, going many years into the past. They know in many cases the different groups associated with the conflict. This is a very complicated situation where you have not just two armies associated with two nation states, but also a number of militia groups that kind of operate like street gangs. They have their own insignia, right? Their own in-group signaling, and a lot of that is reflected in the memes that they produce, which is kind of mind-blowing, right? So there's this big information war happening on the internet, right, between these factions. And again, having that expertise to identify useful sources, to identify useful types of information has been really invaluable. And again, we think there's really nothing like this in terms of a data set for this specific area of research. We've also been sort of briefing the federal government on this too here in the United States to understand, is this relevant to the national security concerns around this conflict, right? So we're constantly getting feedback from external sources as well. And again, this is great coming back to the computer stuff, right? This is a huge data set, right? This is like just a tremendous number of images that we believe to be high quality in terms of the messages that we're interested in. And again, a lot to explore too from both the computer science side of things and the social science side of things, right? It's challenging data to deal with technically, and it's very new data from the perspective of the political scientists. So all those things are coming together in this collaboration.
Great, thanks. So given our timing here, I'd like to switch over to the second part where I believe Daniel's going to dig in a little deeper and talk to us about the algorithms that are involved at the moment and a little bit on why they're so relevant in this collaboration. Thanks, Daniel. Sure.
Yeah. So Walter would drive the slides. So thanks. Yeah. So just to pose the problem, the way we approach it scientifically. So we have as input, and you can, yeah, and we have images that have been questioned, or one question image that you're seeing here, the case we saw before, and we call it query. And we have a corpus of images that we want to consider when we are processing the query and those images to find the images we want to build the provenance graph that we just mentioned. So to do this, our solution is divided into two steps. The first one is image retrieval. It's similar with a few modifications to how Google image search works, or TinEye. So we want to get other images in the corpus that are related to the query. And then in the second step, we have the graph construction where we want to connect the images in a way that we're going to tell the story on how one image gives origin to the other. And as output, we have the provenance graph where we have the explanations. So let's dive into the details of the two parts of the two pieces of the solution, or baseline, the baseline implementation, how we do it. So let's move forward to a quick explanation of how image retrieval works for folks that are not in computer vision or image processing. The way it works for each image that we have techniques from old school computer vision, now from the 90s solutions, where we pay attention to specific regions in the images that have interesting phenomena. When I say interesting phenomena, I'm mentioning corners, edges, blobs, representations of images that in the image that are meaningful. So we have techniques to find these regions, and then we describe these regions, the neighborhood of these regions, the gradients of the values of the pixels, and we generate feature vectors that we call local descriptors. And if we move forward, one of the most famous descriptors is safety, where you detect key points, interest points, you extract them, and you represent the image through many feature vectors. Each feature vector is a region in the image. So the way it works, when we describe the image with these feature vectors, we need to store these in a database, and we build this database of feature vectors where each feature vector points back to the image it belongs to, so it has the address of the image. And this is what we call an inverted file index. So for each feature vector that we have in the database stored, we know what where's the image, or what is the image belongs to. And because we have for each image thousands of key points, and as we're saying, we want to process billions of images, you can imagine how quickly it can escalate for the feature vectors. And when I say feature vectors, in the case of SIFT, we're talking about 128 float, 32-bit float numbers. So it's a huge amount. So we have to index it somehow. The simplest way you can build a KD tree. So whenever we have a query, as we can see in the next slide, we provide the query that we want to get related images. We're gonna extract key points from these images. We're gonna get the feature vectors that belong to the query, and then for each feature vector, we go to the index of feature vectors, and we get the k nearest ones. And because we're getting the k nearest ones from the database, and as I told you, it's an inverted file index, so we know from the nearest feature vectors what are the images they belong to. So based on this, we can get to know for each feature vector of the query what are the nearest images, and we can cast votes. And this is how we build a rank of images. So if we move to the next slide, this is an example of a regular image retrieval of how it operates for Google reverse image search or T9. So you can see on the left the query, which is a bunch of guys that took a picture, and you can see their foot. And then the next images are the rank of images that are related to that one by feature vectors, by the key points. And you can see the first one is suspiciously similar, but it misses some of the guys. So you're not seeing, for example, if the guy with white shoes that's missing, yeah, so you can see here that it's not there. So what is the message here is that regular image retrieval is not enough for provenance, because in a regular image retrieval, we could not get the source of the guy that has the white shoes. So because of that, we have a provenance image retrieval, which is in the next slide, where we have extra steps for getting those images. So we don't want only the images that are directly connected or share content with the query, but the ones that share content transitively. So the way we do it, we can get the first two images that we had before and make what we call a homography transformation, or do registration, and compute their difference and focus on the guy that has the white shoes. So if we go to the next slide, we have an example of one of the data sets we use. So you can see here that this image, they share background, but the first one has an ostrich. And with regular image retrieval, it's easy to provide the first image and get the second one, but we will not get the source of the ostrich. So if we use techniques that we have from computer vision for registering the images, and if we move forward, we can highlight the regions that are different. It didn't move yet. Yeah, there we go. And then we can query only the key points that are on the regions that are different. And with these, we can get the sources of the ostrich. So with these, we can get the images, all the images that we need for doing provenance analysis. Moving forward, we can see what happens when we apply the context incorporation. This is the method we call for doing this second query. So you can see in the top the regular retrieval. And then the second one, you can see the mask that we generated in black and white, with white being the regions that are different. So we can query on the key points that belong to the white regions. And then as you can see in the rank on the bottom, you can see that the second image, after doing provenance image retrieval, you can get the source of the guy that has the white shoes. So with this, we can get all the images that we need for, or most of them that we need for building the provenance graphs. Moving forward, yeah, and just showing that that's the shared content. Okay, so we improved the results. So moving forward, this is an example of that explains why it is it's hard, because some objects are really small. So if you go to the next slide, we're just highlighting what are all the pieces that share content from other images, and we have solutions that we developed for dealing with these small objects. And moving forward, we go to the next step, which is building the provenance graph. So the first part that I just talked about was getting the image that we need. The second one is building the provenance graph. One of the ways that we can do it is, okay, you have a set of images, including the query, and you can analyze for every image pair, you can analyze how they share key points. So you can match the key points. So you can see here, for example, in the case of Kurt Cobain and BIG Guy and other image, that they share 7 matches here. So it means they have shared content. And whenever you compare images that do not share content, which is the next case on the bottom, you will see there are no matches. So if we build an adjacency matrix for all the images, for all the pairs, and we express how many matches there are there, so we have here the assumption that the more matches the images share, the more content they share, the more higher connection they might have. So this is in the case, if we go to the next slide, you're going to see the adjacency matrix. So what we can do, we can build the adjacency matrix for each pair of each possible pair of images combinations, and fill this adjacency matrix with the number of key points. And based on our assumption that images that are related will present more key points, one simple way that we can build the provenance graph is using a maximum spanning tree algorithm to find the maximum spanning tree. So we can use cross-causal pring to compute the provenance graph, and it leads to very interesting results. So this is our simplest solutions. Of course, we have other solutions where we use different data. We use metadata, or we use even deep learning for comparing patches of images using some metric learning to give some order to the images. But this is the very basic solution. Moving forward, yeah, so this is our basic solution, and this is how we can build the provenance graphs and get interesting results. But of course, there is space for more research and collaborations, and this is what I want to bring right now to the group. So first thing is, if you get the metrics that we use to measure the quality of the graphs we're generating with this simple solution I just mentioned to you. So these metrics, they were proposed by NIST, and this is related to their data set that is well behaved, and they generated different versions of the image, and we have the ground truth. So we know the graph of the manipulations, so we can compare that graph. We can compare that graph with the graphs we generate from our solutions. So when you compare these graphs, you can do it in terms of nodes, how they match, and in terms of edges, and in terms of the graph, which is a combination of both. As you can see here, we do not do really well on the edge overlap. So these metrics, they should be between 0 and 1, where 1 is perfect, and 1 is perfect. And you can see that 0.27 is far from 1 for finding the edges and connecting the images. So we have a lot of space here to improve these results and get better examples. Another open problem that we have is for video, as just mentioned. So you can see here an example from some Disney cartoons where the frames, they are completely different from each other in terms of appearance, but in terms of action and dancing and movements, which is something that is inherent to videos, they are very similar. So the characters, they are dancing in the same way and following the same steps. So this is not provenance in terms of the appearance of how the frames look, but it's in the video and how actions are being executed. And this is something that we should be looking into in the future, because this is important for intellectual property protection and also tracking down how your work is being used. Of course, in this case, they all belong to Disney, and it's not a big deal. But if one of them belongs to another company, that could be a problem. Next case is a funny case that we had here just recently in Notre Dame. Of course, we love football here, and our coach, the ex-coach, he left Notre Dame and went to LSU, and he took with him some of his videos, and you can see that they were reused, and we could leverage video provenance analysis to find these cases. So you always have him in Notre Dame, and then after he went to LSU, the videos are being reused and for in other contexts. So they kept him and changed it back around. Another other examples. Yeah, please.
If I could interrupt for a moment, we did have two questions come through that I think would probably make sense to answer before moving to into the video part. So there's a question about the examples that you've shown that create forged images by combining multiple images. They'd like to know if the other scenario is if it's handled. wherein you take an existing image and then you extract features to create, multiple forged instances.
Yeah, I suppose. Yeah, that's the case when you have an object that was portrayed and you remove the object. Let's say you removed somebody to. You didn't want that person or that object, so you have another version where something is missing. So Provenance works for that too, because we match the image, so we will be able to match the background and then find there is a difference of the object that is missing. And this is one of the challenges that we have in Provenance. So whenever I have this case, when an object is there, was it removed or was it added? So we have techniques where we can figure that out. One of the ways is looking at the metadata, for example. If one image is older than the other, and the newer one is missing that object, so we have a clear case of removal. So yeah, it works for those cases too.
Yeah, I'll note just on the topic of metadata, we don't always trust that though, because that's very easy to change. That said, in the wild, not many people go through the trouble of actually changing it. So we think anyway, but that's kind of like, not a gold standard, reference point. It's like a bronze standard.
We always take metadata with a grain of salt. Yeah, it's important. But that's funny how folks forget about it. And even thumbnails, sometimes you have the altered image and thumbnail is the original one, so you can use that. Yeah.
So then, question from me. I'm just thinking here, do you guys incorporate, or would you incorporate like a data augmentation approach to try to address like the different ways that a given image could be, modified? So like you might data augmentation to remove parts, and make multiple images, or you might use data augmentation to make an amalgamation of images, deceiving character.
That's a good question. We have a paper that we published just last year where we did this. So we got patches of images, and we made perturbations after a number of transformations. Let's say after 3 transformations, and the other one after 10 transformations. And we're training metric learning neural networks to learn how to compare these patches and give them an order. So we would be able to know, okay, this patch is closer to this one because it has less transformations than the other one. And for this method, we're doing what you just suggested. But of course, there is space for more transformations. We use a small set of transformations, and it's always something that is worth doing investigations and also figuring out what is a good representative of operations that we could use. That's a good question. Yeah.
Okay, great. Okay, and then another question that came through, well, more of a statement, but I'll posit it as a question. Are watermarks effective to try to protect against this sort of thing?
They are not, because whenever you do operations, the watermark will be destroyed, especially the global ones, right? And that's the nice thing that makes Provenance complementary to the PIFD that you just mentioned, because those are tools that they analyze the images as single assets and alone on themselves. So whenever you have a manipulation and even a change or watermark, it's able to detect in the pixel values what's going on. But Provenance looks in a set of images and tries to find out what is the information they share. So it's even if you added a watermark or if it was destroyed, if it shares some content and some visual content, Provenance will work.
Yeah, I'll note too, on the internet, it's common to take screenshots of things and then use that as a base image, right, to manipulate. Yeah. And that's a real challenge for watermarking. Most watermarks do not survive a screenshot. Some are designed to, but their effectiveness is not perfect. And so that's a major confound as well. Yeah. Another thing too, in terms of the survivability of watermarks, repeated applications of compression, which is very common as these images are uploaded again and again to social media platforms that automatically do this, right, to save on storage. So, yeah.
Okay, and Ari follows up with, there's been a fair amount of research on transformation preserving watermarks lately. So maybe that would be something good to talk about offline after this talk.
Yeah, sure. Yeah.
Yeah. Yeah, I mean, obviously watermarks, that's still an active area of research. I mean, there are lots of commercial products out there in that space. And again, a classic problem, especially the recapture aspect of it. And again, as Daniel mentioned, it could certainly like sort of play a part here somewhere, right? Again, if like it survives in some manner.
Right. Okay. So then we have a question from Josh, who I believe I know the answer to this one too, but you guys go ahead. So he's asking if there's a more reliable method to determine whether an image is a source image or a resultant than just looking at metadata. I believe
that's a good question.
Yeah.
Yeah, and it reflects on what I just mentioned in the slides, that in terms of edge overlap of the metric where we compare the edges were not that great. So we are still doing research on this regard. And as I mentioned, we developed a solution where we rely on neural networks and provide patches, and we trained the network to use metric learning to compare these and find out what is the direction of the link between the patches, and then figure out for the image. But this is something that is still ongoing, is an ongoing research, an open problem. Yeah.
Okay. And then one last question. Dr. Ghoshal is asking if the research only addresses image merging, or can it be extended to detect other operations done onto the image, such as pixel manipulation or blurring?
Yes, it does. So either local operations or global operations, it works for both of them. And yes, so it does. So
Right.
if I have blurring and of course we are not in the point, and this is a good point, where we can identify the operations. So this is it's one of the extra steps for provenance. So besides linking the images and telling the order of how one gives order to the other, being able to name the operation, so saying, hey, it was a blurring, or it was so this is something that would increase the explainability of the output of the provenance graph. But yeah, it works for global operations too.
Okay, great, thanks. All right, you can continue then.
Yeah, and to conclude the next steps that we are looking, and I just want to highlight Bill's work, and he has just recently joined us as an intern. So we are looking for how to apply these for viral content clustering. So we had a previous experience, and Bill was really important in this work, and collecting data from the 2019 Indonesian elections, where we had memes, and memes, they share content in a different way, as we just mentioned. So it's not like the news data set where it's very naive and the content that's shared is near duplicate. So it's more on style or different things, small objects. So we have some research, and there's a lot of space for working on this type of content. And in the next slide, and also we collected some data from the Russo-Ukrainian war, and also we are checking how we can cluster this content and see how they are related and what they are trying to convey. And of course, this material is not sharing near duplicates, but sharing style and information.
Yeah, and these are some examples too from the data set I mentioned, right? That Jason highlighted as part of the collaboration.
And another thing is the way we approached the provenance so far was most like a post hoc thing. So okay, we have the events or have the data, and we analyze the data. Another question is, can we do this in a more proactive way? So can we plug these in a stream of images that are being sent? Let's say this is content that's being shared in Telegram here. Can we have it running there, and then finding the trends and pointing out important aspects that we might need to understand? So this is something that we are interested in doing too. And of course, the last one is scale. So yeah, always space for improving the performance and increasing how much data we can process. As I mentioned, the basic one, we process pairs of images, and this processing can be done in parallel, but still we always need to improve the performance and have results faster and faster.
Yeah, I think there's some vision here of processing this data in real time. You know, as images are uploaded, right, they're analyzed, and that's a significant hurdle. Right, as I mentioned, right, the largest social media companies have no infrastructure to do this, given the state of today's algorithms. So there's got to be a lot more work done in the efficiency of the algorithms, right? Like distributed computing, right? Supporting the analysis. There have to be some better ways to do all of this, and we're just not quite there yet. But I think, again, this is a really interesting aspect of the research that combines both the system piece and the computer vision piece.
I think there's also interesting work to be done in situations where you have organizations that want things to be air gapped. So, they're not going to want a social media organization or whomever doing their image provenance analysis. They want something that can be done on-prem or at the very least on like a cloud instance somewhere. Do you see that happening? Like, I'm thinking also like defense.
Yeah, exactly. Yeah. So we hear this quite a bit from our government partners. In fact, we were just having a discussion about, should an analysis algorithm go to the internet to like assist in the analysis, or is this really locked down, right, due to security concerns? Yeah, I mean, the federal government has a lot of concerns about the security, and also, again, like who owns the infrastructure, right? Should it live in the cloud, right? Does it need to run on a classified network, right? All of these things are in play here, right? Especially if you get into the national security aspects of this type of work.
Mm-hmm.
Also affects too the scientific integrity project, right? I mean, a lot of those are government conducted investigations, right? Where that must be in-house, right? You can't have that leaking to the public internet in any way, right? Like very, very sensitive cases involving, right, like careers and grant money and all these different things.
Mm-hmm. Okay, thanks.
Should I summarize, or do you want to? There's one more slide here.
Oh yeah. This is a wrap up of what we just brought today. So yeah, our intent was to highlight how it's hard to deal with visual information, but we have taken provenance analysis, and we showed you some of the algorithms we have developed, the basic ones. Of course, we working on developing more and more, and also we would like to issue this as a challenge and bring more people to join us in the endeavor and prove it.
Yeah, I'll note too, one challenge we didn't really talk about here directly is the interpretation of the messages. We're also working on that as part of another DARPA research effort. And that, I think, is even more challenging than the scale. Like, I think the scale can be solved with some pretty straightforward engineering, but to interpret a message like a human does is a very sophisticated AI capability that does not exist in any useful way yet. So that's another pretty interesting direction here. And again, it has pretty big consequences for the political side of things.
And when you say interpreting the message, I mean, if I think of memes, then you'd start at the text level, but I assume you're also talking about interpreting what the intent was of.
Yeah, exactly. So coming back to some of these examples that Bill's been looking at, right? So you can see, again, these are from the Ukraine conflict, but oftentimes you see like a Western style meme trope being used, right? Like the Yes Chad meme in the middle panel. So there's a funny joke, just like a surface level reading will reveal. And if you stop there, you don't understand the meme, right? Because again, we're familiar with this content. There's often, again, some message that you get when you think about it and contextualize it, or you're part of the in-group and you get the real joke, which is different from the surface level message, right? That's how humor works in many cases. But what's interesting here is the disinformation is piggybacking on the humor, right? It's part of the joke delivery. And that's really, really tough. So again, there are a lot of NLP techniques that are being used here that are, surfacing a bunch of stuff that like is irrelevant, or like they're completely miscategorizing it because of the way the joke is constructed. And that's the problem. It's even more of a confound if there isn't any text, right? You can't easily identify, say, a meme genre, right? Like the panel here on the right, we see some flags, we see events happening, but what are those events, right? That means you need to have some familiarity with current events, what just happened in the news, or the history of a particular place. Who is in these scenes, right? Do we need to bring automatic facial recognition to bear on this problem to identify known people, right? And then we can get some sense of the context they've appeared in the past, right? And reason through what's going on there as well. So all of that is part of the current algorithm development in this area.
Okay, great, thanks. So I didn't get a chance to ask this, but I thought it might be useful to ask. Where open source fits into this. We talked about open data sets. I mean, open data sets are out there and they'll permit more detailed research, but you know, what's Notre Dame's thoughts on, and Loyola's thoughts on being involved, you know, in projects that follow open source principles?
Yeah, we're in this lab. We're definitely 100% like open source, open access. We love getting this stuff out there. I mean, we're university researchers, so we're not trying to sell any of this. Yeah. It's much more useful to get this out to other people that can use it. I think what's interesting here with these algorithms too, it's not just the research community that's interested. There are a bunch of other stakeholders. Like I mentioned, we're working with political scientists, right? If there's, say, computational social scientists that can bridge these two areas, it'd be great. Again, get these algorithms in the hands of the people that, like, you know, can do some interesting work beyond what we're doing. And then again, if companies want to use this too, that's great, right? If Google came to us and said, you know what, like, we do want a piece of this to put into our code, it's out there, right? We're not putting restrictive licenses on any of this. Same thing with the data too. You know, it's like as we finalize our data sets, we release them open access, right? It's freely available. Anybody can take the data and do work on it. So we very much love the, you know, the spirit, you know, behind Red Hat as a company, right? Because that's the kind of thing we do on a daily basis.
Okay, great. Surprisingly, I've run out of questions, but looking to the chat here, does anybody have any final things they'd like to ask Walter and Daniel?
Surely there's a question or two still out there.
I don't know, guys. I'm hearing crickets. So
we're going to stop the share then.
I have shared my email in the chat if anybody inside or outside Red Hat would like to discuss.
Oh, wait, there's a question. Can we get the GitHub link? Absolutely. In fact, I think, were the links in the talk? If not,
did we have the book chapter?
Yeah, so what we'll do, we can add that so it's just a little bit more explicit. And we're going to share these slides with the Red Hat team here, and they'll be distributed in PDF format. So we'll make sure we include that in case folks want to take a look.
Yeah, and if anything seems to be missing, particularly talking to Dennis here, I included my email in the chat. I'll include it again with the tag to you. Please hit me up, and you know, happy to provide and to talk about things further.
Yeah, there's also a project page for this on the research website. So if the GitHub information should be there. And we'll be sharing the slides and video after this talk. I put a link in the chat for which page that is, but if you don't remember, just go to research.redhat.com and look for Provenance. And there aren't too many projects with Provenance in their title, so it's easy to find this one. So I'd really like to thank you, Walter and Daniel. This was a really interesting talk, and thank you for all the preparation, and thank you for sending us Bill to work with us in the summer. He's been a really great intern to have. And thank you, Bill, for answering all the questions in chat. You're the power behind the scenes. And last of all, Jason, thank you so much for leading the conversation and bringing in all the good questions and making up a few of your own as well while we did this. Really appreciate everybody's attending and asking questions, and feel free to contact any of us if you're interested in following up on this work.
Great. It was our pleasure to do this. Thanks, everybody.
Yeah, thank you.
Bye-bye.
Bye-bye.